quantum frontier shaping tomorrow.
The quantum computing. First of all, we all know computers get better and better all the time, no matter where we are in the cycle. Moore's law now going back 60 years, and some say even before that, in the way computing was done, if you go back to include counting, adding machines and early computers, and even an abacus, there's where you can say the amount of power it took to compute something. As the power requirements go down, the computational power goes up. And the big one that when Gordon Moore came up with this law was the price of the silicon and what you can do with it would go down. And so that's something that all projections say pretty much levels out somewhere about 2023, 2024. Read this decades ago. It's still there, but the law remains. That law is that about every 18 months, the amount of computational power doubles and the cost of putting it on silicon goes down. Right now, we've got chips that are at about 3 nanometers. And at 3 nanometers, compare this to 100 nanometers not that long ago. Most of your common equipment that you see now, your cell phone, your home computer, whatever, is at 5. And there's a lot of 3s. The new cell phones have 3 nanometers. And what a nanometer is a very small measurement. But at that level, you start talking about only being one or only a couple atoms thick. And so when you try to pass signals over that, you're going to run out of atoms if it gets any thinner. So they're looking at other things happening. One of the big promises for the future to continue this Moore's law effect of getting more and more power is quantum computing. And it's because it fundamentally changes how we measure computing. So let's put it real simple. Quantum computing is to take a digital computer that has a 0 and 1, like a light switch on or off, and add to that the idea that it can be both on and off at the same time. And that adds up to a qubit, which is off, off, on, and on. There's 4 states just by one, let's say light switch, because that's something we can all easily picture. When you think of being able to have 4 positions, not just on or off, but also more on and more off, or both at the same time, those kind of, however you describe that, to form a qubit. And then you start adding up more and more qubits, like computers went from a single bit processor to 2, 4, 8, 16, 32, 64, and the architectures of how the chips are put together are based on that number of bits. And each one exponentially grows how big you can grow the computer. And now with being able to fundamentally change that by more, it just seems going from 2 to 4, but you're really going from everything that we've accomplished and being able to start right at the beginning and multiply that out each time by that much. Right now, they're building quantum computers in very strict conditions of very low temperatures, very isolated, very clean, big rooms that are functioning only to have a little bit of quantum computing going on, and getting that down to just the quantum thing. They tend to make mistakes. We'll get back to that in a second. And growing them has been a little bit tougher. Now they're up to 50 or 100 of these qubits put together. What it does is it's able to do compute much faster, exponentially, and then it's like exponential times exponential fast. It's growing faster than anything we predicted with Moore's law, and it's able to grow a long ways from where they have it right now. The limitation right now is that temperature problem, keeping things cold.